Hello everyone, so this is the solution video to Worksheet 3.4. We're going to be talking about complex numbers and how we can do certain types of arithmetic and solving equations and finding zeros that involve complex solutions with an imaginary part. Okay, so for number one, we're first going to just kind of consider how we can do the arithmetic involved with adding, subtracting, multiplying, and dividing complex numbers that have imaginary parts. So for part A in number one, we're going to take these two numbers, z and w, and in this case subtract z from w. So what we're looking at doing here is taking the number 2 plus 7i, and from that we're going to subtract 3 minus 5i. Now what we want to do here is we want to sort of group the parts of these two complex numbers in terms of getting the real part together, which is a, and then the imaginary part, which is b times I. So in this particular case, once we go ahead and distribute the negative there, so we have 2 plus 7i minus 3 plus 5i. So we can clearly see here that the real parts are the 2 and the negative 3, and the purely imaginary parts are the positive 7i and the positive 5i. So we're going to go ahead and we're going to group those together. So this is not something you necessarily need to do, but I think it's good to see. If we were to put the real parts together, we'd have 2 minus 3, and then we'd also have our imaginary parts, which are 7i plus 5i. So what we're looking at here is this is the a plus, and then this part right here, this is the b times I. So after we do the necessary arithmetic, what we end up with is we end up with the number negative 1, which is a real part, plus 12 times I, which is our imaginary part. And that would be the proper form for this particular value. Okay, so let's try a similar thing down here with z times w. So we'll take our number z, which is 3 minus 5i, and we're going to multiply that with w, 2 plus 7i. Now when you're doing things like adding and subtracting, you kind of get a flavor for this with that first one. You almost treat the terms that have the I as if you were combining terms that involved a variable like x. Even though I is not a variable, it's specifically defined, we treat it as such in how we multiply, add, combine like terms and things of that nature. So we're going to look at this and think about how we would do this if maybe this was 3 minus 5x times 2 plus 7x. What we'd do is we'd multiply this out, all the terms. So let's go ahead and do that. Again, I'm going to write it out maybe a little bit more explicitly than needs to be done if you were doing this on homework or tests, but I think it's good to see. So we'd multiply first 3 times 2. Then we would take 3 and we would multiply that times 7i. Then we would take minus 5i, multiply that by 2, and then we would take the minus 5i and we multiply that times positive 7i. So we're just distributing this out and multiplying. And let's see what we get here. So this is going to give us 6 plus 21i, and this is going to give us minus 10 times i. And if we multiply minus 5i and 7i, we're going to end up with this minus 35. Again, think of this as if these were minus 5x and 7x. That would give us minus 35i squared. Now, with the I squared, you should hopefully remember that since we had defined I as the square root of negative 1, if we were to square that, we'd end up with just negative 1. So negative 1 is equal to I squared. So in terms of this value here, we can continue on and say, well, this is going to be 6. I'll leave these uncombined for now. 21i minus 10i, and since that I squared is just negative 1, that's going to make this plus 35. And now we just go ahead and we combine our constants, we combine our imaginary terms, and we end up with 41 plus 11i. And that would be our answer to part B. Okay, now C gets a little bit more complicated. And as we set this up, we know that we've got, all right, well, this is our 3 minus 5i up top. And then down below, we've got 2 plus 7i. Now, the thing we have to watch out for here, or take note of, is that recall that this may not seem like an issue. This might seem like, okay, I'm done. This is a simplified number. But recall that I is actually a radical. It's the square root of -1. And as such, we don't want to have this down in the denominator. So lots of times when we had radicals in denominators, we wanted to rationalize in order to get it out of the denominator. And we're going to do a similar type of thing here. So recall that this is a radical. So we rationalize the denominator. And in this case, what we're going to need to do is we're going to need to multiply the top and the bottom by the conjugate of the bottom. So we multiply top and bottom by the conjugate of our denominator, which is 2 plus 7i. In this particular case, the conjugate is going to be 2 minus 7i. So to get the conjugate of a term like this, you just change the sign in between them, and that will work out. Let's see how this works for us. So if we go ahead and do this, we're going to have 3 minus 5i over 2 plus 7i, and we're going to multiply the top by 2 minus 7i, and we're going to multiply the bottom by 2 minus 7i. And the reason we need to use the conjugate here is that that's going to guarantee that we don't have any traces of radicals, or in this case I, left over on our denominator. So we're going to go ahead and multiply out the top and the bottom. If we do this, we're going to get 6 minus 21i minus 10i, and then we'd have plus 35i squared. And then in the bottom, we're going to have 4 minus 14i plus 14i minus 49i squared. And we recall that the I squared is essentially just -1. So we've got 6 minus 21i minus 10i minus 35 all over 4 minus 14i plus 14i, and then we've got plus 49 in the denominator. So we see in the denominator the minus 14 and the positive 14i are going to cancel out. We can then combine the 4 and the 49, and then up top we combine our imaginary terms and we combine our real terms, and we end up with is we're going to have minus 29 minus 31i all over 53. Now, we were asked at the start of this problem to put all numbers in the form a plus bi, so we're going to go ahead and we're going to do that. One way that we could possibly do this, and you probably should be comfortable doing either. One way to write this is we could actually take that 53 and put it out front and just say, well, this is 1 over 53 times minus 29 minus 31i. That kind of fits the profile. Another way we could do this is we could actually split it up into two numbers. So we could have minus 29 over 53 minus 31i over 53. I think either of these would be okay. This one, I guess, is a little bit closer to what we were asked to do, but I have a feeling that WebAssign sometimes wants wants it to look like this. So just kind of keep your eyes open for that. Okay, so that's how we do arithmetic with complex numbers. Next, we're going to do inevitably simplification of radicals plays into this section, and I think we'll get some good practice with these two. So we're asked to simplify the square root of negative 49, and I think it helps to think about what's really going on under this radical. Again, if we were just asked about real numbers, this is not a real number, we move on. But if we are going to take into account the possibility of complex solutions, then we might want to be comfortable simplifying this. So what I would like to do is kind of think about what's going on under that radical in terms of factors. We could think of that minus 49 as negative 1 times 49. And since we've got a product under this radical, we could rewrite this as the square root of negative 1 times the square root of 49. We can do that for multiplication and division. We can't split it up that way with addition and subtraction. It has to be multiplication. So since those are factors under there, we can break it up as two separate radicals. And now we can look at this and see, well, we've got the square root of negative 1, which we know is I. And then the square root of 49 actually is a perfect square, and that's just going to be 7. And we get in the habit of writing this as 7 times I. And that's usually the form that we like these numbers to take. So it's a purely imaginary number. A little bit trickier, but same type of thing with the square root of 18, negative 18 rather. Let's go ahead and think about this. And what we want to think about is, well, we've definitely got a negative 1 as a factor under there. So we can kind of pull that out. The other thing we want to see is if there's any way that one of the factors of the remaining number would be a perfect square that we could sort of pull out of this. And if we look at 18 and we think of the factors of 18, 9 times 2 should come to mind, specifically because 9 is a perfect square that we're then going to pull out. So we could break this up as 3 different radicals: the square root of negative 1 times the square root of 9 times the square root of 2. And this is going to be the same as I times 3 times the square root of 2. That's not going to simplify any further. And again, the way that we'd like to see the form of this number take is conventionally we'd put 3 times I times the square root of 2. We like to keep those numbers out in front of the radical, because if we put them behind, sometimes it gets a little bit confusing. So this would be how we'd want to simplify that. Okay, so now if we move on to number 4, we're going to be looking to find real and complex zeros of polynomials. Real zeros we've talked about. Real zeros, we've got a few techniques, and we've also got the fact that real zeros can be viewed as x-intercepts of the curve of a particular polynomial. But when we get into complex zeros, we don't really get to see those visually on graphs, at least on an xy coordinate plane. So they're a little bit trickier to deal with, and we have to kind of rely on algebraic techniques to do that for now. So let's go ahead and take a look at this. We want to find the zeros. Our technique for finding zeros is we take the function, in this case x squared plus 1, and we set it equal to 0, and then solve for x. It's a quadratic. We could definitely use the quadratic formula. It's not necessary in this particular case. Probably the easiest way to approach this one is, let's go ahead, get x squared on one side, and let's move that constant to the other. So at this point we could see, well, let's go ahead and take the square root of both sides. If we were to take the square root of both sides, we'd get that x is equal to plus or minus the square root of negative 1. And we know that the square root of negative 1 is just going to be plus or minus I. So that gives us 2 complex zeros. And since the degree of this polynomial is 2, it's a quadratic, those are the only zeros we're going to expect to see, because it's going to cap out at two zeros. And in this case, they're both complex. So if we then wanted to factor the polynomial, we go back to what we talked about in previous sections. And since we consider that since x equals I and x equals negative I are zeros, the factors would be x minus I and x minus negative I are factors. So anytime you've got a 0, you can always find the factor by just taking x minus whatever that 0 is, and that will end up being a factor of the polynomial. So we can conclude that f of x, if we were to factor this, would be equal to, actually, f of x equals x squared plus 1 can be rewritten in factored form as x minus I times x plus I. And that would be the factored form. And again, if we were to graph this, since we don't have any real zeros, we wouldn't see any x-intercepts. We'd see a parabola that never hits the x-axis. And lastly, we've got the same type of thing. We want to find any real or complex zeros and then completely factor the polynomial. So let's go ahead and take the same approach. We are going to take x squared minus 4x plus 13. We're going to set it equal to 0 and then solve for x. In this particular case, factoring is not really going to be an option for us, and the quadratic formula is going to probably be the way to go here. So we identify our a as 1, we identify our b as being minus 4, and we identify our c using 13. So again, what we're going to do here is we're going to use the quadratic formula. So given these values, we know that x, our solutions or our zeros, x can be equal to minus b plus or minus the square root of b squared minus 4 times a times c. And all of this goes over 2 times a. So now our only work really is to kind of simplify this a little bit. So we're going to have positive 4 plus or minus the square root of 16, and that's going to give us a minus 52, and then a 2 in the denominator. So we've got 4 plus or minus 16 minus 52 is going to give us a negative 36. That's going to be nice and easy to work with, over 2. And again, with this square root of negative 36, we could think of this as the square root of minus 1 times 36, obviously, and 36 is a perfect square, so we've got square root of negative 1 times the square root of 36, which is going to give us 6 times I. So we can use that in our solutions. So we've got 4 plus or minus 6i divided by 2. Almost there. So we want to get it in the form a plus bi. Let's split this up into 2 separate terms. So that's going to give us 4 over 2 plus or minus 6i over 2. These are going to simplify nicely into 2 plus or minus 3 times I. And those are our 2 zeros. So if these are our zeros, now we want to completely factor. And just like we did last time, all we're going to do is we're going to say that our function, f of x, when multiplied out is x squared minus 4x plus 13, can be factored as x minus, so we pick one of these 2 zeros. Let's start with just 2 plus 3i, and actually, yeah, this will work, times x minus the other 0, which is 2 minus 3i. You could distribute that negative if you wanted to, but I think leaving it like this is probably just fine, because the nice thing about this is it's very clear what the zeros are in this case. Alright, so that does it for this set of solutions, and I will see you all in the next video.